All right. Today we're going to finish out chapter 17. Just a reminder, we do have a test coming up. Chapter 17 is going to be the last chapter on the test, so the test is not next week, but it's the following week. Next week we've got a couple other things planned, but we'll discuss those next week. So we're still talking about equilibrium. And the last section, section 3, it's all about using equilibrium constants. So for the last couple of classes, we've gone through how to set them up and things like that. And hopefully at this point, it's not too complicated. Remember, basically, so start with our products. And we put the reactants on the bottom. Okay. So, at this point, hopefully that's pretty straightforward and you can do it pretty quickly. So, the first thing that we can do, and honestly, this isn't really new, but it talks about it in this section, so we'll just go over it really quickly, is basically calculate equilibrium concentrations. And the only real difference is that in the previous section, you were given the concentrations and asked for the equilibrium constant. Now you'll be given the constant and you'll be given the constant, and then you'll have to figure out at least one of these concentrations. In this example, let's actually look at that. So it gives us this reaction. Okay? And it gives us a little bit of background information about hydrogen sulfide and things like that. But at high temperatures, we can get hydrogen sulfide to actually decompose, and it forms hydrogen gas and sulfur. So what we're dealing with that. Now you'll notice that it is homogeneous. They're all in the gas phase. So it goes on. The problem gives us some useful information. It tells us that the equilibrium constant, 2.27 times 10 to the minus third. And then what we're actually calculating, so what is the concentration of hydrogen gas? So we want to know what that concentration is. If it gives us the concentration of the sulfur gas, 0.0540 moles per liter, and our hydrogen sulfide, 0.184. Okay. So we need to set up our equilibrium expression. So we have K. Start with these over here. these. Got the 2, that, 2 with that, right? So that's our equilibrium expression. So we have 4 different pieces, and the problem gives us 3 of them. So it gives us that our K value, that, gives us the concentration here. And it gives us this. And what we're trying to figure is that. So for this, we are going to need a little bit of algebra. We need to move things around, but we've been doing that all year, so hopefully that's fairly routine at this point. So what we're going to end up with and we're almost there when we get to this point. I do see students that stop at this point. The problem is we want to know what the concentration of hydrogen gas is. The way this is set up is telling us what the concentration squared is. So we need to take the square root of both sides, and that is what we are actually going to be looking at. So that algebra is probably the hardest part of this whole problem. So, I mean, like I said, algebra is just part of chemistry, so hopefully it's not too much of a struggle right now to do that. So now we can just start filling things in. We fill in the K, fill in the sulfur, the hydrogen sulfide. Order of operations, making sure you don't hit a key wrong, okay? It happens. Even sometimes when I'm going too fast, I'll hit a key wrong. So slowing down is worthwhile. But anyway, so we just have to put that into our calculator, and we get that our concentration H2 is 0.0377. And if you want to double check your work, make sure that you've done it correctly. If you take these values plus the one that you calculated and put it in here, you should get this. So if you want to double check, make sure that you didn't do algebra incorrectly or hit a button wrong. So you can't double check that. But really, that's very similar to a lot of things that we've been doing all year with, algebra. Just you have a certain number of things in the problem, you'll be given all but one. So let's move on to something a little bit different, a little bit new. It uses the same basic principles, but we're going to be dealing with solubility, dissolving something. Solubility actually is an equilibrium situation. That's, I guess, the word I was looking for. There are some things that dissolve really, really well. Have a really high solubility. You can dissolve a whole bunch of solute into the solvent for example, salt. If you're trying to dissolve salt in water, you can dissolve a whole lot. But then there are other things that are only a little bit soluble. Of course, we want to be able to measure. Okay? Now, when we deal with solubility, obviously, in order to write an equilibrium expression, we have to have some sort of reaction written out. Well, the nice thing is, you just really have to break these ionic compounds apart. Okay? That's really what we're going to be dealing with is ionic compounds. So if we look at salt, sodium chloride, all we have to do is break it into the ions. Okay. Now this, to go back and write the phases, is going to be solid, but these are dissolved, so they're both aqueous. Of course, that means for our K expression, we don't include this in the K expression because we don't include solids or pure liquids. So our K expression, and instead of writing EQ to show that this is solubility, you write SP. It's the solubility product. But we write it exactly the same way. Okay, so we would do the concentration of the sodium ions times the concentration of the chlorine ions. And of course, if we have that right there, because it is heterogeneous, like we said, we take it out. So that is our KSP. The nice thing is, if you're dealing with KSP, you know that you're dissolving something, which means we have a solid, or I guess you technically can dissolve a liquid. We probably won't really deal with those. I don't think we've ever seen one in the book where they are dissolving a liquid. Either way, we just ignore it when we're writing our KSP. And we just put these things because concentration can change. So, then we can go on, just like all of our other K values, they are determined experimentally. To find the KSP, we would measure the concentrations. I'm sure that there is a value of KSP for sodium chloride, but the only time that we ever really work with KSP it's with things that don't dissolve very readily, things that are not a lot is going to dissolve. Okay? And so, because sodium chloride dissolves so well, we really don't worry about the KSP because the value is going to be very large. Instead, we're going to look at things that have very small KSPs. Not very much is going to dissolve at all. And like I said, these are all experimentally determined. And there's a table on page 615 with a whole bunch of solubility product constants. And if you look at them, you'll notice they're all very small numbers. Let's see. The smallest of which appears to be this iron hydroxide, the FeOH3. 2.8 times 10 to the minus 39th. So that barely dissolves at all. But it does measurably dissolve, so we can calculate a K value for it. How would we use these K values? Well, the example that the book gives is with barium. Okay. If you are trying to take an X-ray, but you're really interested in like the stomach and the intestinal tract, the X-rays are a little bit tough because they don't show up really well because they're soft tissues. But if you drink barium sulfate, they show up really well on the X-rays. The problem is barium sulfate is actually a toxic substance. It's poisonous. But we can give this barium sulfate to patients because the KSP is so small that only a tiny bit is actually going to break apart. And that means most of the product is actually just going to flush through the system without actually causing any problems. Okay. So we can use this a couple different ways. Let's go through some examples here. Example problem 5, calculating molar solubility. So it says use the KSP value from table 3, which is the one that we were just looking at, to calculate the solubility in moles per liter of copper carbonate at 298 Kelvin. Once again, temperature does make a difference. Table 3, you notice, says at 298 Kelvin. So all of the problems and things like that will be at 298 Kelvin. So, all right. So we have copper carbonate, which is Cu. Markers down. Let's look what we got. Some new ones somewhere. I had some new ones. Where did they go? Where did they go? Okay. Well, that's not good. We'll make do with these for now. I'll have to get some more. There, that worked. Okay. So we've got our copper carbonate. And so we set up our reaction. And we're going to have to break apart this ionic compound. And this is a polyatomic. So if you are still fuzzy on breaking apart ionic compounds, then go back and just go over that chapter again. But that's what we're going to get. Now, if you don't get the charges right. The good news is the charges aren't really going to make a difference for this. So since you're given this, you pretty much just have to figure out where it's going to break apart. Now we write our KSP expression. Okay. Remember, this is the solid. These are the aqueous. That's why these are in here and that's not. Okay. And it says to use the KSP value from table 3. And the KSP value is 2.5 times 10 to the minus 10. But that's all it gives us. It doesn't tell us one of these. So here we have this problem because we have 3 different things, but it only gives us 1. And up until now, it's always given us everything except for 1. And at first glance, you might think, well, how am I supposed to figure this out? Because I have 2 variables. Well, the trick is, if you look at this, okay, every time I get a copper ion, I'm going to get a carbonate ion as well. So every time I get one of these, I get one of these, and it's the same going the other way. I cannot get one of these without getting one of these. And what that tells us is the number of copper ions is the same as the number of carbonate ions. So if these have the same number of particles, they're going to have the same concentrations. So what we can do, we can say, okay, the concentration of Cu2 plus is equal to concentration of the carbonate fix this here. So those concentrations have to be the same because they're coming from this. And if we set that equal to X, then we can say that the KSP is equal to X times X, or KSP is equal to X squared. And if we want to know what X is, we take the square root of KSP. And at that point, we throw that in there, and we take the square root. Okay. The square root, when we put that in our calculator, it's 1.6 times 10 to the minus 5. So X equals 1.6 times 10 to the minus 5. And that is our concentration. So that is the trick that we need to remember, is that these are going to come apart in a very specific ratio. Okay? Now they do the next problem, example problem 6, with magnesium hydroxide. And it's pretty much the same thing, but the important thing to remember is that when we have magnesium hydroxide, it's going to break apart into 3 three different pieces. So when we're at our KSP, we have that, which means the concentration magnesium is equal to, well, not exactly the same as this because we get two of those. Okay, so this turns out to be half the concentration of ROH. So we multiply that. Okay, because this we get two for every one of these. So we have to multiply this by 2 to set them equal, which then means that we can take the concentrations and say 2x for magnesium and x for the hydroxide. X is still going to be our concentration. It's just we know that magnesium is going to be twice whatever that is. And that's why we can use the same variable. So we get 2x times x squared. Okay. So that is what we're going to be using here. Okay. I wrote that backwards. It's like that doesn't. We have x there. We're going to put 2x here. There we go. That looks better. Because whatever this concentration is, that's twice what that concentration is. So there we go. That's what I wanted to do originally, but then I second guessed myself. Anyway, so whatever this concentration is, that's twice as much. So that gets the 2x. So we have x times 2x squared. So we have x times 4x squared. So KSP is equal to 4x cubed. And it gives us the KSP in the problem, and then it's just algebra. So. We are going to talk about precipitates. And we talked in the beginning of the year about precipitation reactions. Precipitation reactions are when you have two aqueous solutions, mix them together, and you get a solid. We are going to take some time to figure out how we can predict whether mixing these two things are going to create a precipitate or not. It's all based off of what you're mixing and the concentrations. Okay. And we use the KSP, okay, because that tells us, KSP tells us how much of some compound we're able to have dissolved at one time. And really what's happening in a precipitation reaction is when we mix it, we're creating a new compound, and the KSP is small enough that it can't still stay in solution. It has to fall out as a solid. Okay. And the way we do this we look at the KSP of the new thing that we could create. Okay? Now we have to look at what we're mixing to figure out what's going on. Okay? And then we compare the KSP to something that we call the QSP. Now the QSP is exactly the same as the KSP, except K indicates that we are at equilibrium. Q is our starting conditions. Okay, so that probably doesn't really make a lot of sense yet. But let's do an example, and we will see if we can clear this up a little bit. Okay? So, example problem 7. Predict whether a precipitate of lead chloride, okay, so that's going to be important. We're looking for lead chloride, will form if 100 milliliters, so we've got 100 milliliters of sodium chloride solution at 0.0100 molar. And we're adding it to 100 milliliters of lead nitrate at 0.0200 molar. Okay. So we need to figure out some concentrations. Okay. Now, the thing is, it gives us concentrations to begin with, right? These are concentrations. The problem is we're changing the volume. Okay. As soon as you mix them together, you've changed the total volume. And if you change the volume, you change the concentration. So we have to figure out what the new concentrations are. There's a trick though. If you have equal volumes that you're adding, you just take this number, divide it by 2. Because you've doubled the volume, which halves your concentration. Now, if it's not equal, then you have to do a little bit of stoichiometry type problems. I guess not really stoichiometry, just some unit multipliers really, where you have to figure out, okay, how many moles did I add of this, and what's our new volume? So, but since these are the same, our new concentrations are going to be that and that. Okay. We mix them together, it changes the volume, so it changes the concentration. Okay. Now, we need to set up an equilibrium expression. So, when we're doing this, obviously, this is an aqueous solution, so these ions have broken apart, and these ions have broken apart. And we can set up KSPs for both of those, but we don't care, because those are already dissolved. We care about this. Okay? So this ion right here, plus this ion right there, can form that. And what we need to do is write out the equation for this. So lead chloride can separate out like that. And so our KSP is equal to the lead ion times the chlorine ion squared. Now remember, I said QSP was the same, it was just at a different time. So the QSP is also equal to this. The difference is KSP, like we said, when everything comes to equilibrium, that's the total concentrations that it can hold. QSP, that's our starting conditions. Right? It's what we have right at the beginning of the reaction. Okay? So what we do, we take these new concentrations that we have at the beginning of the reaction and we put them in our QSP. Because we need to find what is the QSP beginning of the reaction. So our lead, time, make this look a little nicer. So we have the times squared. Just put that in our calculator. And we get 2.5 times 10 to the minus 7. Now, how can we tell whether or not a precipitate is going to be formed based off of that number? Well, it's not like the K where we said if it's less than 1, you get more of this, and if it's greater than 1, you get more of something else. There's no absolute number that you're looking at. Instead, we want to compare it to the KSP. So we can look that up, or sometimes the problem will give it to us. So the KSP for the lead chloride is 1.7 times 10 to the minus 5. And so we want to know, is the QSP bigger or smaller than the KSP? And that's going to tell us our answer. Okay. And the rules are right there on the top of page 619. If the QSP is less than the KSP, no precipitate forms. Okay. This number is less than that number. So in this situation, we're not going to get a precipitate. If the QSP is equal to the KSP, you're right at the saturation point, but you're still not going to get a precipitate. Once your QSP is bigger than your KSP, when you mix them, that solution, that volume of solvent is not able to contain that much of whatever it is you've mixed, and so you get a precipitate and you form the solid. Okay. This right here, that's the trick to remember. When you mix things, you change the volume, which changes the concentration. Okay. Now you're not changing how many moles you added, you're just changing the total volume, and that's what changes the concentration. If you have equal volumes, it's super easy. You've doubled the total volume when they mix, so you just have to half the concentration. If you don't have equal volumes, it's not that hard. You just have to figure out, okay, this is moles per liter. I can figure out based off of the volume how many moles there are. So I know I have how many moles of this. I can do the same thing here. And then I find what my new total volume is, and moles divided by the new total volume. Okay. If you were to do that with this, you would get the same answer. It's just, it's easier if we know we have equal volumes. So. Okay. There's one last really quick principle in this section, and I know this section has sort of been a big one. We've been taking all of these different concepts that we talked about all chapter and sort of said, okay, use them. but we just have this last little thing. It's called the common ion effect. And basically, what it is so common ion means you have two things that both, when they dissolve, are going to create the same ion. So if we go back and just look at our lead chloride, like we had in the last problem, okay? Now we can look at the KSP and it'll say, okay, we can dissolve this amount of lead chloride in a given volume. But if that water already had some sodium chloride, well, they have this common ion, chloride. What that does, if you've already dissolved sodium chloride, it means you can dissolve less of this. Because even though the solution could hold more of the lead ions, it can't hold any more of the chlorine. So no more of that can dissolve. Okay. Basically, if you have two things that are going to create a common ion, you can dissolve less of them together than you could if they were separate. It's kind of like, you know, here in the classroom, you have tables. If I had a mixture of just like the red chairs that are here and black chairs, okay? If all the spots are taken up by red chairs, then we can't put black chairs. It's just kind of what's going on here. You already have one of those ions in solution. You are not able to dissolve as much of the other one. Okay. And you can use that with Le Chatelier, like if you really want to, well, if you had lead chloride that was dissolved, you put sodium chloride in there. Well, sodium chloride is more willing to dissolve than the lead chloride, so you can sort of force it out. Or you can, you know, prevent something from dissolving instead of forcing it out. And it's just kind of, you know. So that's the common ion effect. Really, that's as deep as you need to understand it. So don't stress. It's just if it has the same thing, you can dissolve less. And that's the end. So really, it's been a lot of taking the stuff that we learned in the first two sections and sort of putting a different twist on them. We introduced this concept that solubility, dissolving, is also an equilibrium process. So we can write an equilibrium expression for it. We use SP to tell us that it's solubility instead of just a normal equilibrium. And we can take advantage of the fact that when we dissolve ionic compounds, they're going to dissolve in very, very specific ratios, however many ions are in the formula unit. And so we can use that and apply that to our algebra to figure out a couple of things. And then the last thing, just with the KSP, QSP, precipitation, if you calculate the QSP and it's less than the KSP, well, there's plenty of ability to dissolve everything, but if it's greater than, the solution cannot hold that, so it comes out as a precipitate. So, all right. Well, we do have a little bit of homework on this. So hopefully, if you have questions, go ahead and ask. But yeah.
What lesson is this?
We're still in 17. This is the third. This is the third one in 17.